Somewhere in continental Europe, a large generator suddenly trips. In an instant, supply falls below demand, and the electrical heartbeat begins to slow. No human has time to react first. Across the grid, automatic reserves are already moving, before most people notice anything has happened. You cannot see this balance, but you can measure it. Across continental Europe, the grid's frequency is designed to stay close to 50 Hz. Think of it as the rhythm of the entire system. When generation and demand match, that rhythm holds steady. When a large generator disconnects, demand briefly outweighs supply. The vast rotating machines connected to the grid give up a little of their stored kinetic energy, and the frequency starts to fall. That fall is not immediate, because the grid has inertia. Many large turbines and generators are already spinning with enormous momentum. When supply suddenly drops, those machines slow slightly and release stored kinetic energy into the grid. It does not solve the imbalance, but it buys the system precious seconds, enough time to detect what changed and begin the automatic response. Now the grid begins its first correction. In continental Europe, the first line of defense is called Frequency Containment Reserve, or FCR. It is automatic. When the frequency falls, selected reserve providers increase their power. When it rises, they reduce it. In continental Europe, FCR is designed to fully activate within 30 seconds. Its job is not to return the system to normal. Its job is to stop the fall while slower reserves take over. FCR buys the grid its first seconds. Then a second layer begins. It is called Automatic Frequency Restoration Reserve, or AFRR. Grid control systems adjust selected generators, batteries, or flexible demand during the following minutes. Its job is to bring frequency closer to its target and release the first emergency reserve. If the disturbance continues, a slower manual reserve called MFRR brings in larger changes. That layered response is why one generator failure does not automatically become a blackout. But the margin is not unlimited. If frequency or voltage moves outside safe limits, protection systems begin isolating equipment to prevent damage. In a severe disturbance, operators may deliberately disconnect part of the network. It is a controlled sacrifice. Lose a small area to stop a much larger cascade. The system that kept the grid stable for decades is now changing faster than ever. Older networks were built around enormous turbines, each one spinning with the physical momentum of a freight train. That momentum, called inertia, slows a sudden change in frequency and gives operators time to react. But wind, solar, and batteries connect through power electronics. They can respond extremely fast, but they do not all behave like a giant spinning machine. As more of the grid changes, keeping those first seconds stable becomes an engineering problem of precision. This is where grid-scale batteries become more than energy storage. Their control systems measure grid frequency continuously. When demand suddenly exceeds generation, a battery can inject power within fractions of a second. When there is too much generation, it can absorb energy instead. But batteries do not create unlimited electricity. Their job is to stabilize the first critical moments, buying time while slower reserves and power plants take over. In the modern grid, stored energy and fast software are becoming part of the machine that keeps the lights on. Keeping the grid stable is not only a national job. Across much of continental Europe, power systems are connected, so electricity can move between countries when conditions change. Some connections operate as part of the same synchronized AC grid. Others are high-voltage direct current links, called HVDC interconnectors, which can precisely control how much power crosses a border. These links are not unlimited, and they are not magic, but they give operators options. A region with surplus generation can support another region facing a shortage. In seconds, the grid becomes a coordinated system, measuring, deciding, and moving energy to where it is needed most. After a major outage, restoring electricity is not as simple as turning everything back on. Large power stations cannot always restart without power from the grid. A black start unit can begin independently, often using a small generator or a hydro unit, then energize one section at a time Operators gradually reconnect lines, plants, and demand while watching voltage and frequency at every step. The recovery is slow on purpose. Restore the grid too quickly, and instability can return. Long before a fault happens, the grid is being balanced minute by minute. Forecasts estimate tomorrow's demand, wind and solar output, and the availability of each power plant. Generators are scheduled. Reserve capacity is held back. Operators prepare for the difference between the plan and reality. The goal is not simply to make enough electricity, it is to have the right amount in the right place at exactly the right moment. Because on a power grid, even a small mismatch between supply and demand must be corrected before it becomes a larger problem. The grid also has physical limits. Heat makes power lines sag, storms can damage equipment, and a single transmission corridor can become a bottleneck, even when enough electricity exists somewhere else. That is why reliability is built through redundancy. Multiple routes, reserve units, protective relays, maintenance, and constant monitoring. The system is strongest when it has options. The future grid will depend on more sensors, faster control systems, batteries, and stronger connections between regions. But technology does not remove the laws of physics. Electricity still has to be balanced every second. The challenge is to make a cleaner system just as stable, or more stable, than the one it replaces. Most of the time, the power grid is invisible. A light turns on, a train moves, a hospital stays running, but behind every normal second is a system measuring change, responding to faults, and restoring balance before most people notice anything at all. That is what keeps the lights on. And that balance is becoming harder to maintain. Electricity demand changes constantly. Factories start, trains accelerate, homes switch on appliances, and weather changes how much power wind and solar can produce. The grid must absorb all of those changes without letting frequency drift too far in either direction. That is why reliability is not one machine or one power plant. It is the ability to react, coordinate, and recover every second of every day. The power grid is one of the largest machines humanity has ever built, yet it has no single owner, no central battery, and no pause button. It survives because thousands of machines, sensors, engineers, and automated systems work together every second. The next time a light turns on, remember what happened before that moment. Electricity was generated, balanced, transmitted, monitored, and protected. All fast enough that you never had to notice. For most of us, electricity is invisible until it disappears. But every light, screen, train, and hospital depends on a machine that never stops balancing. The grid does not sleep. It reacts, and for now it keeps the world running.